right, now we're going to take a look at what these values of Kc actually mean. We come up with these numbers, but what do they tell us? Well, we have to remember that this is products over reactants. So if the products are on top and the reactants on the bottom, and you get a very large number for that, and I'll define large later on, right? A very large number for that. That means you got a whole lot of products and not very many reactants, which means the reaction is going mainly towards the products, whereas the color going mainly to the right. If your value of K is really low, like 10 to the negative 12th or something, that means you have more reactants than you have products, which means then that the reaction is going towards the reactants, which is towards the left. So very small values means the reaction is going mainly to the left. A little bit on the right, but mainly to the left. Then the area between 0.01 or 10 to the negative 2 and 100 or 10 to the positive 2 is that gray area where you have a mixture of both of different amounts, but enough where it's not considered to be overwhelming in one direction or the other. So we say that those are basically at equilibrium, as opposed to being completely done on the left or completely done on the right. So when we look at values, that's what these things are telling us. How much is actually completed or going or not going at all, or all mixed up in some degree of continuity there. So we're going to look at something called a Q value, which is a test for what Kc, or as it's calculated the same way as Kc, but it's a test in terms of comparing whether we are at equilibrium or not by comparing it to the Kc. So these are all things we're looking at and thinking about as we do these problems that we have for practice. So let's take a look at some odd number problems in your book. This is on page 685. Problem number 32. We're given this reaction where we are going from HI to HU and I2. All the gases phase in order for this to use K, or A because we could have, but these are all gases. The value is 1.84, which is basically really close to being at equilibrium. Just probably a tad more reactants in products, but not much. But now the question is here, what is the value of K for the reverse reaction? All right, now remember when we talked about this before, that when we have the value for this, we know that this is H2 times I2 over HI squared. Okay, so this is going to be HI squared over H2 times I2, so they are reciprocals of each other. So the value of K for this is going to be reciprocal of 1.84, which we can write as 1.84 to the negative 1 power. And the value we get for this is 0.543. And this is telling us, hey, you got, the way this is written right here, you don't have as much product as you have reactants, but it's very, very close. So it's going mainly to the left here. This is saying 1.4, slightly, I mean, it's equilibrium, but it's slightly going to the right, but not much. We just basically say these are both in equilibrium, just a tad in one of the two directions. And number 35 on the same page, we're given equilibrium values for the concentrations of a particular equilibrium reaction. We know that we're asked to find the Kc here. This is just a plug and play problem. All we have to do is plug in these values. So PCl5 is 0.0158. Oh, and this is in a 5-liter vessel. My mistake here. So we got one extra step. This is supposed to be moles per liter. That's just moles. So we're going to divide both of these by 5 liters. So we end up with moles per liter for our label. which is what we need. So when we do the math on that, we get 9.25 times 10 to the negative 3. We get 0.0174 is moles per liter. And we get 3.16 times 10 to the negative 3 over 3. I hate writing zeros, so I'm going to use silent notation. Now all we have to do is plug them in. So that means then that this value right here, the PCl5, goes right there. The Cl2, 0.0174, goes right there. And the PCl3 value, this right here. Oh, I so hate this more. PCl. Oh my goodness. I truly hate the board. This is black already. Oh, there's a good one. We got this. And 4 more years. You and I, buddy. 4 more years. Alright, so we plug in those numbers there. And our calculator gives us a value of looks like we haven't done here, so let's do it real quick right here. So we got 9.25, oops, clear, 3.16, E negative 3 divided by 9.25, E negative 3 divided by, because they're both in the denominator, 0.0174. And I get 19.6. So it's still that range of between 1/100th and 100, but because it's bigger than 1, we can pretty much surmise it's going mainly to the right direction. But, you know, that's just a very, very close value to 0. Now we get into what those numbers are telling us in extremes. Now when I say extremes, I mean, when we talk about this reaction right here, the nitrogen oxygen, by the way, this is the next page over in column number 49, when you pause your video to get caught out. For this right here, because the value for NO squared over N2 times O2 is your Kc, and that value is 4.6 times 10 to the negative 31. That's a decimal point and 30 zeros and then a 4.6. Just a very hint of a movement to the right. The fact that it's very, very small means it's virtually all reactants and no products. So is this nearly a complete reaction? Heck no. Not even close. Over here, however, this is this reaction here, which is going to be C2H6 concentration over concentration C2H4 times the concentration H2. We get this number right here, which is a 1 and a 3 and then 20 zeros behind it with a bunch of commas, probably about 7 commas. And that means that it's virtually all products and no reactants. So, yes, this is a nearly complete reaction. Number 51, now we deal with that Q that we were talking about. Q is a test for Kc. Now, you find it exactly the same way as a Kc, but then you compare it to the Kc value to see if you did indeed have a mixture at equilibrium. How do we know? Well, we compare it to this. If our value for Q is this number, this set of data that's given to us in A or B or both would be at equilibrium. But if it's not, we have to determine which way the reaction is going to shift to establish equilibrium. That's something called the Chatelier's principle, which we'll get into at the very end of this chapter, and it was talked about by Mr. Anderson in the video that you looked at before we started the first one. So we plug in these values. So that means then that we're going to have, now you got to be careful of these squares here. That gets forgotten so often. And I'm as guilty of that as anybody else. 0.062 squared times 0.0123 divided by 0.0720 squared. And when I worked that out, I think I worked it out, yeah, I got 6.23 times 10 to the negative 4. Well, we compare that to KC, which is 3.07 times 10 to the negative 4, and that is greater than KC. But you want it to be down to KC, so when it shifts to go to equilibrium, it's going to shift to the lower side, which is the reactant side, so that's going to shift left. And then we get smaller, not a whole lot, it's not going to take very long to do it, but it's got to go back down to 3.07 times 10 to the negative 4. Do the same thing here. This is going to be 0.0159 squared times 0.0139. I don't put labels there because we don't have labels in the answer, so you don't have to worry about that for this. And then the denominator is 0.121, and that's squared. So I punched that in my calculator, and when I got it off the floor, I saw that the answer for that was 2.40 times 10 to the negative 4. Compared to that, you see it's just a little bit less, so this is less KC. That means this value has to be larger, which means we have to have more products, less reactants, so that's going to shift towards the products, which is on the right-hand side of the arrow. So it'll shift right. Okay? So those are the types of problems that you're going to be dealing with in this assignment. Your practice problems. 34, 36, 50, and we do number 54, just do A and B. All right? Have fun.